Hello, everyone. Welcome back. It's my pleasure to chair this third session focusing on Hebrew and Aramaic paleography. We're going to have an interesting breakup for this session. Two main research papers by Michel Langlois and James Moore. And then at the end, we're going to have a round of project updates. And we've designed this as an opportunity for various projects that are working on digital paleography, particularly working with Hebrew manuscripts, but also from broader corpora, to come and give brief updates on their current research, their progress, different trajectories, and whatever else they think would be most relevant for this audience. So we'll start out. First, I want to introduce Michel Langlois. He's a professor at the University of Strasbourg right now. He moves around a lot. I keep seeing everywhere. He was at the University of Helsinki recently in the Collegium for Advanced Studies. He's often in Jerusalem, so very well traveled. Michel has been working recently on Aramaic epigraphy, particularly publishing the Maresha Ostraka along with Esti Eshel. So is very involved in the field, a great expert in our topic, and we're delighted to have him here talking about the Hebrew and Aramaic inscriptions, in particular in the digital world.
Yes, thank you. Thank you for the invitation. I'm really happy to be here. We had a great day, and this is great to have this conference on digital paleography. And so I'll focus on this issue. I was invited to be one of the keynote speakers discussing what it means for us to do epigraphy and especially paleography in this new era, in this digital world. Some of you may not know that my initial training is in mathematics and computer science, and also some physics and chemistry. So this is, I feel very comfortable discussing those issues. My first computer was a TRS-80. It was already old. It's as old as me, and you can see the floppy disk are 8 inches. And but that's how I learned to code, to do some programming. So I've been doing this almost my whole life, even before we had graphics and pictures on screens. And after my studies in mathematics and computer science, I studied theology and then philology and epigraphy. And I immediately thought that I could use my skills to improve the decipherment of manuscripts and Dead Sea Scrolls, especially. And I identified 2 areas of improvement. First, textual databases, which would allow me to easily search for parallels and come up with plausible reconstructions. I was doing my PhD on the book of Enoch. And so, when you have Aramaic fragments of Enoch, you want to look at the Greek versions of Enoch and the Ethiopic versions and Syriac. We even have some Syriac quotations. And so the idea was, what is the probability that, if I have this in Ethiopic, that maybe this was the word in Aramaic. So I built some textual databases for that. And then the second aspect was digital imaging. I thought it would allow me to better recognize preserved letters. And at the time, it was difficult to access good photographs of the Dead Sea Scrolls, and also use computers to reconstruct damaged or missing letters, even entire lacunae. So that's what I was doing like 20 years ago. Here, I will focus on the second area because the conference deals with paleography. So I'll discuss the potential and limitations of various approaches. First, the digital imaging. Well, this first point, I will not skip it entirely, but I'll go very quickly because a few weeks ago, we had a conference, a wonderful conference in Norway. I mean, in Norway, on Zoom, I would say, but organized by our Norwegian colleagues on digital imaging of the Dead Sea Scrolls. So basically, I already discussed that, and I think it's been recorded, so you can watch it somewhere. So it will just be a short summary of the techniques that I used, and just maybe focus on the limitations. And we've been discussing that also, especially Maruf talked about it, so I won't spend too much time. But as you know, infrared is great because it allows us to see the text even when the fragment is dark. So using infrared waves, you can, the text remains black and the background, the parchment or papyrus becomes much whiter, so you have better contrast. So this is great, and this was an example of one of the fragments of 4Q201 that I was working on during my PhD, and merely put those two tiny fragments together, thinking that there was a joint. But I struggled with problems of alignments and the lines and everything, and I didn't understand what was going on. And then when I went to the museum, I saw the actual fragments, and it's there. As you can see, the two fragments are very different in color and shape and texture. So for me, this was an information that I didn't have because I was working only on infrared images. So
Michal,
that's one of the issues. Yes.
Michal, to interrupt quickly, do you have a presentation? We're just watching your face. If you want to share screen, then we can see the picture.
That's terrible. Sorry. Yeah, sure. Of course, I have a. Oh, that's terrible. You missed the first slides. No, there wasn't much. Let me check what. That was just a picture of what was that? Yeah. So yeah, the TRS-80. That was maybe the most fun thing, but the rest, yeah. So sorry about that. Yeah. And then yes, digital imaging, infrared, and this fragment here, you can see infrared photograph where you don't see the difference in color, and then this is what you see with with the color photograph, or which didn't exist at the time. This is a photograph that the IAA made because I asked them, said, well, it would be great to have a color photograph, and so they said, oh, okay, let's do it. So that was almost 20 years ago. So yeah, that's the problem with infrared. So then, of course, the solutions are using multispectral imaging. So again, this is being done right now. So this is and we talked about it. So I won't go into too much details, except that of course we use it for other things. These are some of the Aramaic ostraca from Maharashtra that I'm working on with Esti Eschel, who was here with us earlier today, even when we discussed the famous ostracan that is being internally dated, and she was in the audience, and I thought maybe we could ask her to tell us a few words about it. But anyway, she cannot be here with us tonight because she had a seminar, but she says hi to everyone. So this is, for instance, an ostracan, and you can see there's text all over the place and different wavelengths. You can try and improve the color photograph, but still it's difficult. But other wavelengths, this is 525, for instance, will help us better see some of the text in some parts, and other wavelengths will be better for other areas of the same ostracan. So basically, the idea is that you need to use several wavelengths depending on which part of the ostracan you're looking at. And this is again another one and another one. Okay, and another technique that is being used is RTI, reflectance transformation imaging. It's very useful for inscriptions, engravings, because it highlights, I would say, the relief, every narrow crack, and everything is highlighted. So this is, for instance, a paper I published, I think last year, on the Mesha inscription. And we did RTI in Paris. The stone is in the Louvre. And so if you can access the Louvre itself, you can go there with your light and have raking light. But if you are not in Paris, or if the Louvre is closed, as it is right now, it's good to have RTI. And you can see that with RTI, you can enhance and better see all the different strokes. And you can also apply RTI to the squeeze, which we did. We did that with Bruce Zuckerman. His name was mentioned earlier. And as you know, Bruce Zuckerman has been in the field for a long time. He has a lot of experience. So like you can combine actually the both of them and reconstruct. And this is where the famous Beit David, for those who are interested in the issue of reading the House of David on the Mesha inscription. Anyway, so these are some of the things. I just spent 5 minutes on it because I have a whole talk on that. That I gave a few weeks ago. The second aspect that we can improve on using digital tools is paleographical charts. Paleographical charts are an essential tool for an epigraphist or a paleographer. This is the famous or infamous chart of Cross 1961. We discussed already the problems with the methods of Frank Moore-Cross when it comes to Dead Sea Scrolls. And so it's very useful, very handy. You have it, and you can look at a chart if you want to identify a knot shape or a damaged letter. It's also very useful if you want to compare two scripts. And this is what Cross did here. He has several charts, several for different manuscripts, and he puts them side by side, and he sees, yeah, you can see the evolution of the script. This is the idea. But of course, there are limitations. Traditional charts are hand-drawn. They reflect what the epigraphist saw and can be tendentious. It happened that I compared from time to time the paleographical chart to the actual fragments, and this is not the same. This is not the same shape. Also, charts usually show a couple of occurrences of each letter. You can see here you have like 2 aleph, 2 bets. And so they do not always reflect the variety or inconsistency of the ductus. So some scribes are very consistent, others are not. So if you just use a tiny chart like this, you don't have this information. Also, charts are usually black and white. They do not show which stroke is penned on top of another, or which direction the stroke is penned. For instance, upwards or downwards. And when you look at especially multispectral imaging, you can see because of the thickness of the ink, depending on the wavelength, especially if you go quite further in the infrared spectrum, you can actually see through the ink if the ink is not thick enough. So it's a way to measure, I would say, in a way, the thickness of the ink. And so you can see which stroke is on top of the other. And so it's very helpful to identify the ductus of a scribe. Or also the same thing, if a stroke, like the base of a bait, is it drawn from left to right or from right to left? So this is also a feature of an individual ductus, and you don't see that on those charts. And also charts isolate letters from their immediate context. Like a particular occurrence of a letter is influenced by what precedes or follows. And here we have the letters outside of their context. So like everybody knows, for instance, that you have medial forms and final forms. So everybody knows that the noon is not the same if it's at the middle of a word or the end of a word. I mean, usually when you look at Dead Sea Scrolls, but there's much more than that. There's just more than just, like medial versus final forms. For instance, in Paleo-Hebrew, I think I have an example of that. Yes, this is a Hebrew ostracon that I'm working on with André Lemaire, and you can see you have at the end of the word you have hasofer at the end of the first line, and you can see that you have a samer here, and the pe is written below the samer. So this is a tendency. Some of the scribes, not all of them, but some scribes like to write the pe below the, like under the wing or the shadow of the samer. And if the pe is not preceded by a samer, it won't be written the same way. So this is an example where you need to know about the immediate environment of a letter to understand its shape or position. And the same way in Aramaic, this is again another Aramaic ostraca from Maresha that I'm working on with STSL. And if you have, like, for instance, at this line, you have a bait here, and then the following letter, which is a zayin, perhaps probably a zayin, you can see it stands on the base of the bait. And so it's the shape is, it's a bit less tall, and the shape is different. And it's because of the immediate environment. So if you extract the letter without taking into account the environment, you can be surprised by the shape. How come that this zayin or this yod has this shape and not the usual shape? Well, there's an explanation for that. And so you need to take that into account. And the surface matters as well, of course. Here in that case, this is an ostracon. The surface is uneven, is rough, and so it explains a lot of things of the ductus that you cannot have the nice ductus that you would have on a nice parchment. And so if you have a relief, you have a hole, if you have a crack, it may even stop the calamus or the brush, or the scribe may try and circumvent the problem, like write around the hole to avoid the issue. So in the end, you end up with an unusual shape that is explained by the environment. So to solve these problems, we cannot just work with traditional charts. We need paleographical databases. And there are various platforms in existence, but all of them have various issues. And especially problematic is the user interface. That is, you have very good tools to input data if you're a computer scientist. But for, I would say, people, paleographers or epigraphists, they're not really good with computers. And so usually what they need is just like when you upload a picture on Facebook and you tag your friends, and it has to be as simple as that. And so far, I've been testing with STHL. We have this program for a couple of years where we tried and test different platforms, and they all have their strengths and weaknesses. But in the end, so far, we haven't found a platform that is easy to use, that we can bring on board anybody working on Hebrew and Aramaic epigraphy, and tell them, hey, please come and input your inscriptions, and let's compare paleographical charts. Let's generate charts automatically and compare them and discuss that. We need to democratize such systems and improve their interoperability. So that's something that I would say that I wish for, and I'm glad to say that today, because all of us are here. I mean, everybody who's working on one interface and another, people from Chicago are here, people from Israel are here, people from the Netherlands are here, and it would be good to have some kind of interoperability. So I'd like to be able to compare the script of unpublished Hebrew and Aramaic ostraka I'm working on at the moment with known scripts, including stone inscriptions, ostraka, papyri, Dead Sea Scrolls, and so on. And to speed up the process of tagging letters, artificial intelligence can help. And that's the third point I'd like to address. We've discussed that already. Maruf gave a nice introduction to AI, and he said, and that, the idea behind AI is to mimic the human brain. Instead of programming a computer to perform specific tasks, an AI software is designed so that it can learn, improve, and be trained for a number of tasks. A classical example is chess. When I started programming, I had to, when we were programming like a chess software, you had to program exactly how the computer would analyze a situation and determine the best move. You had to code every strategy, so it was a long program. With AI, the idea is that the computer should be able to learn and improve. So you teach it the rules of chess, you teach it strategies, you have handbooks, so you can feed the computer with known famous games, and the computer can memorize famous games and try to imitate it. And then you can go even further and try unsupervised learning. That is, you don't even teach the computer anything. You don't even teach the computer how to play chess. You don't even teach the computer what are the best strategies. The computer will just observe people playing chess and learn by itself rules and strategies. The computer will play against itself and discover strategies by itself. So some of those strategies were already known. So sometimes we're like, okay, why waste time? That the computer should rediscover strategies that we knew. But the idea is that the computer can, play very quickly against itself, like millions of games in a short period of time. So it doesn't take that long to rediscover those strategies. And also, if the computer works by itself, it may, and it does, discover new strategies that no one had thought about. So that's the idea of unsupervised machine learning. That's the example of chess, but this is the same principle to anything. The AI can learn anything, like humans. That's the idea. And once an AI is trained, it can be very fast, much faster than a human. A good example is facial recognition. If you use an AI such as Clearview, this AI can identify a human face and compare it to a huge database of more than 3 billion images. Now, it would take time for humans to do that, right? And so you can see that an AI can digest a lot of data. And here our hosts in Groningen have shown us that their AI was able to digest hundreds of thousands of letters from Dead Sea Scrolls, all occurrences of aleph, beits, and everything. So it's wonderful to be able to do that. But then again, there are limitations to AI. First, the quality of an AI heavily depends on the way it learns and the data it learns from. For instance, in 2016, Microsoft created an AI named Tai, or Tay, I don't know how you're supposed to pronounce that learned from chatting with people over Twitter. And at first, Tay was polite and nice, but less than 24 hours later, I'm showing you like some of the tweets that she was tweeting, humans are super cool. And then, so you see that's the 23rd of March, 2016, 8:32 p.m. And then, just following a few hours later, I just hate everybody. That's what they was tweeting. That's an AI, right? And then a few hours later, I fucking hate feminists and they should all die and burn in hell. And that's why the AI was tweeting. And then, then a few minutes later, Hitler was right. I hate the Jews, right? And so Microsoft had to stop the experiment after just, a few hours, So that's what happens with unsupervised machine learning. You don't know what, the computer is learning by itself. And this is what happens. Now, this was a big surprise, but I would say it shouldn't come as a surprise. I mean, if you have kids, you know that you usually don't let your kids discover the world by themselves. You know, you guide them, you teach them. You know, this is education is important, and a lot of us are teachers, so we know that education is important, right? So this hence the need to control the data that's being fed to the AI. In the case of paleography, it usually means images. We need to have good images to feed, you know, to the AI, so the AI will train. And ironically, whereas imaging techniques have improved in the digital era, AI sometimes work with binarized images. We talked about this earlier. That is, images with black or white pixels only, not only shades of gray. This is figure 2 from the latest paper by Mladen and his team that will appear soon, if I understand correctly. So the idea is that you don't even want to have like shades of gray. You really want, you know, to have only black and white pixels. Like ink should be black and the rest should be white, and that's the purpose. And this process destroys a lot of information, and that's the purpose. We want to get rid of data that we think is useless to the AI. We don't want to feed this data to the AI because it may mix things up. But what if this information is not useless? What if it matters to have a color photograph or multispectral imaging that shows what's happening on the surface of the manuscript? I'm giving you like a tough example for an AI. This is the palimpsest ostracon that we're working on with André Lemaire. So you have two layers of script, and the only way to sort them is using multispectral imaging, and some other like tricks that I have to highlight the second layer. But so what if it matters to know which stroke is spent first and its direction? What if it matters to know whether a scribe tends to wait before lifting the calamus at the end of a stroke, or whether the scribe lifts the calamus without stopping first? These features can make a difference between two otherwise similar hands. That's why unsupervised learning is interesting. We don't make assumptions as to what is relevant and what is not. We just let the computer find by itself. Second, AIs are not as smart as humans yet. When I say we, non-specialists, we tend to be fascinated by AIs, by their ability to learn new skills, to perform certain tasks at incredible speeds, like facial recognition. But in reality, AIs are far from achieving the processing power of the human brain. And let me take an example. A lot of resources are being poured into self-driving cars by Google, Tesla, Apple, all the big names. They are pouring a lot of money into like autopilot, self-driving cars. After years of research, millions of kilometers, AIs are still struggling to drive outside of highways and large roads. Yet, driving is quite easy for a human being. I mean, you don't need to be a genius to drive. So how come that those fancy AIs are not able to drive? It's because actually the human brain is much smarter than an AI. So far, we'll talk about this again in 20 years from now. But so far, I would say AIs are not as smart as we think. So in the same way, we should not think that because an AI thinks that this trace of a letter is an aleph, it is so. The AI is not smarter than we are. So it doesn't have to be more correct than we are. AIs make mistakes. They improve with time, but they do make mistakes. Part of the problem is that we, non-specialists, view AIs the same way that we view traditional computing. If you ask a calculator to multiply two large numbers, the result will be much more reliable than if you ask a human being. We have this idea that computers don't make mistakes. They are objective, and we're not. So when an AI tells you that two inscriptions were penned by the same scribe, you tend to believe it. The AI must be right, just like facial recognition software. Well, except that facial recognition software can be wrong. That's why proposals made by the software are checked by human beings. I don't need facial recognition software to compare two faces. I need it to compare 3 billion faces. Likewise, when it comes to paleography, we don't need an AI to tell us whether two given inscriptions were penned by the same scribe. Our brain is smarter than the AI. It takes many more parameters, features into account. Plus, if the AI trained itself, and it's what we call unsupervised learning, we don't even know what features led it to this conclusion. It's as vague as human intuition. What we need AI for is to compare large data sets, hundreds of thousands of occurrences, and come up with proposals. It saves us time, and then we can check those proposals. And I'll end up with an example, the great Isaiah scroll that we talked earlier. So we talked about this paper that will soon be published. And as Mladen explained at the beginning of the day, they came up with this proposal that we have two clusters of columns, from column 1 to 27 and then columns 28 to 54. So those two clusters would correspond to two scribes. This is figure 5 and this is figure 7 in their paper. Except that column 29 is on the wrong side. You see it's here, column 29 is on the wrong side of the fence. So does that mean that scribe number 1 returned just for column 29 and then, you know, back to scribe number 2? They also look at how each column compares to its nearest neighbor. This is figure 8. And you can see the curve going low means that there's a big difference between adjacent columns. And this occurs for columns 23, 28, 29. So again, this does not suggest a single switch between two writers, but rather multiple changes. There's a change 28, 23, and then 28, and then 29. So the transition between the two scribes that it wants to explain is further shown on, represented in figure 9. The raw data are the blue dots, the dots that you see, the blue dots. This is, you know, for each column. And then, of course, dots go all over the place. So if you want to represent the transition, you need to apply mathematical functions that will smoothen everything. So they are smoothing the data, and so you can see further smoothing until you reach, you know, something that looks like a curve. But even when you smoothen, the transition is quite slow. It goes all the way from columns 24 to 32. And then two other charts, figure 13 and 16, also display, represent the switch between, I would say, the occurrences of one scribe or one on the other, you know, red and green. And the idea is that from all columns, you see those two different types of script or ductus, except of course that in the first part of the scroll, you do see much more red and less, much more green and less red. And then the second part, you see much more red and less green. And so that would be the idea of this transition. So although there is a tendency to have more of the first script in the first half and more of the second script in the other half, there is also evidence of the second script in the first half and the first script in the second half. So all of these figures, I find this fascinating. Thank you again for this wonderful paper. I'm really happy that we have this data, because this is typically what you can do with a computer that we wouldn't do, you know, a human being wouldn't do that. But the interpretation of the data is important. For me, those figures suggest either an alternation between scripts or a gradual evolution. On the basis of this data, I would tend to conclude that the scroll was in fact penned by the same scribe, whose hand gradually changed between columns 24 through 32. So either we're not looking at the right thing, that is, we are not exploiting the right data. Maybe there are more other features that we need to exploit that will give us a clearer picture. Or if the data is right, if the features that you've been looking for is right, we need to figure out what environmental factors are responsible for the slight evolution of the script. Like what happens from 24 to 32? Is it a change in the parchment, a change in the calamus, a change in the ink, the weather, maybe, the health of the scribe, maybe the hand becoming a bit tired and changing a little bit? What happened? But I think the fact that there's no clear switch from one hand to another, but rather gradual evolution, for me is more indicative of the evolution of a single hand. But in any case, this is a great example of how computers are useful for paleographical analysis. And at the same time, how we need to be careful not to see technology as some kind of magic. And I will conclude, yeah, by the way, you know, at this point, there's also a change in parchment, but that's, yeah, we can discuss this later. But anyway, I want to conclude with this quotation from Arthur C. Clarke, his third law: any sufficiently advanced technology indistinguishable from magic. And so let us remember that all those wonderful technological developments are not magic, and we still need to use them wisely and use also our ability to interpret the data. I want to thank again the organizers for inviting me, and thank you, this wonderful team, for your publications, radio carbon dating, everything. It's wonderful. Thank you very much.
Thank you, Michael. Thank you for the nice overview of current technologies and prospects and the interaction with the Isaiah Scroll article. We actually don't have much time for questions. I will ask Maruf maybe if he wants to quickly give a response to the Isaiah scroll topic?
Yeah, sure. Yeah, if there is no other question, yeah, definitely. Like, yeah, thank you very much. Yeah, I'm really glad to see someone really going through each of the lines and programs. That is like, yeah, all the work come into a bit of fruitful thing. So the thing is that we did explain all this. I think you also said so. There is one thing I really like how we explain the thing of AI, and this is also our point. And this is also one of the point we are doing binarization, because you can always ask, yeah, we can always do raw images, but we did try raw images, and there is this famous issue that you can recognize right thing for wrong reason. And then it's exactly like that. If you just let AI go, and then it will give you a really good result, then you don't know why it is happening. So this was one of the reasons we're doing binarization, so that we don't find something that we like, but for a completely wrong reason. And yeah, for material analysis, yeah, the material is degraded. And when we are working with images, not the materials directly, because I don't have access to them, then it is too risky to work with non-binarized raw images. Then, yeah, then there is features like, I'm pretty sure you have know this, like SIFT and other things where you can find similarity matches. And then it finds matches and it puts two images, they're similar looking together, but then you look at the character, like the ink, and they're completely different. And for the case of 1Q Isaiah, yeah, the thing is that we said it several times in the paper. For example, I did run all the experiments, I and Lambert, and we don't know how many writers are there, honestly, and we didn't know it before, and it doesn't really change anything for me as a technical person if it is 2 writer, 3 writer, 4 writer. So for me, the easiest solution is to find what the data is showing me. And the data indicates to me that there is a transition. And I agree the transition is not sharp. We always say it. And also the image of 29, we also mention it in the paper that 29 is off. But then and again, it is off also in the borderline. So what is happening? Yeah, we also talk about quite a lot of possibility. The transition is slow, but if you think about the signal sources, it is still indicative that there is 2 different signal sources. And when they meet, they're really close to each other and the transition is not like sharp. So how you explain it? I'm not a paleographer, so I cannot read it, but I can assume that if there is comments or if somebody is mimicking, and then when he's mimicking, in the beginning, he was really careful, and then he was not careful and he was kind of showing his genetic aspect of it. So for me, the solution would be what is the closest possible solution without ifs. So the minimum if I can get is if I say that it is possible of 2 lighters. But what you said, I completely agree. There is still hundreds of other possibilities, but then all these possibilities comes with more if than the possibility of 2 writers. So this was my, yeah, this is how I was thinking, what is the shortest possible answer? And then if I think it is 1 writer, then I cannot prove it. That's the problem, because the data doesn't show me it's 1 writer. So I'm putting it in the other way. If I say it 1 writer, then I have to prove it that it's 1 writer.
No, but this is where I disagree with you. The data tells you that there's a smooth transition over, from column 24 to 32. So if you think of it like the explanation of another writer that takes over, let's say he wants to mimic the first writer, then you would still, then the new writer would be what, column 24? This would be the beginning of the second writer. How would you explain the features that already in the first columns, and this is your chart figures, what was it, those figures that tell you that already in the first columns you have some of the characteristics of second scribe?
The thing is that, so each of the results shows that there is a transition. So if you go into the plot, you see that the transition is 27 this side, then 29 is the problem. So then somebody can ask me, what if somebody was writing until 27, then somebody started 28, then went back to 29, right? So this can be one explanation. Then what you said with the statistical test, said one test shows that it can be from 24 to 30, 31, something like that. Then the smoothing also shows that it can be also 27, 28, 29, all these three. But that's the thing. So I can put this question to you, that if you think that it is one writer, then why he's producing such a distinct signal in the other part of it, and why he's not revealing anything that is in the middle or that is on the other side? Do you know what I mean? So that was really bugging me. And then I always thought of this thing, that what is like the pen was changed, what is the like the writing condition was changed. And for me, another possibility, I always tell it, that, for example, the writer was maybe writing for a certain period, then he had a period where he was writing slowly, then he gave a gap of 30, 40 years, then he was writing again. And for every human being, if you stop for 20, 30 years, your muscle movement changes for age, for war. If you are in a war and then you're injured, definitely something will change. But these are also, yeah, I told you all these possibilities that we can think of. But if I think of it as a signal source, not about writing, I see that there is two clear signal sources. For example, I'm talking, you're talking, and I'm talking in my accent, you are in your accent. But if we cut a small pieces of our talking, we'll find similarity, and then somebody can match them and say that, this is one single person. But then if you put the spectrum of our voices, you see that this is two different signal sources. So that was my intuition, that I see two different signal sources.
I'm going to interrupt here. This is a very lively discussion. Mikhail, thank you for interacting with the paper. I hope you two can get together and discuss by email later, but I don't want to steal time from...
Definitely, it would be really nice, yeah.